So we are at the top of the hour here. So we're going to go ahead and get going. Um, First, I appreciate everybody taking some time to sit through this and get a little bit of information about how to select regenerative turbine pumps. They're a little bit different than selecting a centrifugal pump, but not too bad. And we're going to go through some of that stuff here in the next few minutes. This webinar, even though I have it slated for an hour, really only takes 30 to 40 minutes. So we'll get going on this, and it is being recorded, so anybody who wants a copy of it can have a copy of it. A link will automatically be sent to you as soon as it's available. So moving on here. Few quick pumping facts that have nothing to do with regenerative turbine pump selection, but it does kind of give you an idea of how large the pumping world is. So largest pump in the world is the Pentair Fairbanks, whatever that HP 1-4000 numbers are, does 60,000 liters per second, or almost 1 million gallons a minute. But it does that at extremely low pressure, so it only produces just under 2 feet ahead, up to about 16 feet ahead. Head being the amount of water that can be lifted using the pump. So it's a very low pressure pump, but very high volume. Requires over 5,000 horsepower to be able to be driven. Next is the smallest pump in the world. It's 1 nanometer in size. They use it for dispersing medication at a cellular level, and it runs at 18,000 RPM for 15 hours. So just to give you a range of the differences of pumps in the world of pumping, MTH pumps are just a tiny little section of the overall pumping world. Next, we have the highest pressure, and this is important, rotodynamic pump, because there are piston pumps and pressure washer pumps that'll do 20,000, even 100,000 pounds of pressure, but those are not rotodynamic, which we'll look at here real quick. But this particular one does 3,379 feet ahead and requires over 20,000 horsepower to be operated. So that's a pretty big motor. So when we talk about pump classifications, there's basically 2 classifications. You have rotodynamic and positive displacement. Rotodynamic usually means a rotating piece of equipment, where the positive displacement is usually something that moves back and forth without by letting fluid in and then shutting it off, pushing it and letting more fluid in, shutting it off and pushing it. So that's the 2 major kinds of pumps. A regenerative turbine pump falls pretty close to a centrifugal pump. The difference being that a regenerative turbine pump by nature is a much higher pressure than most centrifugal pumps. So we're going to focus on the regenerative turbines today. So what is a regenerative turbine? Regenerative turbine pump is a rotodynamic pump that combines the high discharge pressure of positive displacement pump with the flexibility of a centrifugal pump. Basically what that translates to is that they have extremely high pressure, but they don't have so much high pressure that if you cut them off, they'll blow things up. And I'll get into that a little more here real quick. You should never deadhead a regenerative turbine pump, but you can get pretty darn close without doing damage. Some of the other characteristics of a regenerative turbine pump, besides the high pressure, is that the high pressure is produced usually in just a single impeller. We can do up to 5 stages, which gets extreme amounts of pressure up to 1,000 psi. but usually with just one impeller, you have a compact design as well as simple construction. It's usually just a casing, motor bracket, and the impeller in between, and then the hardware and driver that go to it. They are pulsation free flow. What pulsation is when you have a nozzle and you can see the nozzle that's shooting the water varying as it's shooting. You won't get that from a regenerative turbine. You get a smooth flow that doesn't have any pulsation to it. And our particular model of regenerative turbine pumps have a balanced free floating impeller design because they work both sides of the impeller at the same time. Both sides of the impeller have vanes that keep the impeller balanced. So you don't attach the impeller to the shaft, it just floats. And because all the work is on the outside of the impeller, we also have good NPSH characteristics, which we'll get into some more here in a second. And because of the good NPSH, little to no cavitation, and we do have a lot of different options for configurations and materials. So a little bit about how they work. When you think about a centrifugal pump, which is one of the more common pumps in the world, the water goes in through the eye of the impeller, and as the impeller spins, the vanes grab the fluid, push it towards the outside, and then it goes out the volute and straight out of the pump. So any particular part of the water only gets touched one time by an impeller vane. If you want to build up higher pressure with a centrifugal pump, what you need to have is you need to have multiple centrifugal pump impellers. So you have the one here, and then if you want to get more pressure, you have to put another one in front of it, and so on and so forth, all the way down the line to get that high pressure. With a regenerative turbine pump, instead of having the water get touched one time by each impeller, one impeller gets to touch the water several times throughout the process. So the water is introduced and in the inlet side, and then it rotates over and over again while the pump is spinning. And each time it does this helical water flow, it builds up a little more pressure. So you're, in essence, doing the same act as the multi-stage centrifugal pump with just a single impeller because it's doing it over and over again. On top of doing it over and over again, it's also doing it on both sides at the same time. So with that, you can get extreme amounts of pressure, but not necessarily the same amount of flow. Centrifugal pumps typically have more flow because they are moving water faster, where the regenerative turbine pumps are restricted to the water channel and the act of how it's performing. So we can do anywhere from a half a gallon a minute up to about 150 gallons a minute, and that's about it. So to show you an example, this is your typical Grundfos pump. Each one of these, or each Grundfos pump has multiple stages throughout the impeller or throughout the pump. So they go up for this example has 3 stages up to 25 stages, where our pump has 1 impeller. And so I have laid over our 1 impeller design of our T51 series, a couple different model sizes. Each one of our model sizes is a different number of impeller vanes as well as a different size water channel to control what the performance is. With the multi-stage centrifugals, they add stages to make the pressure go higher. So even when we're hitting the 25 stage mark here, we can still cross that over with just a single impeller of our T51 here. We're going to look into some more details. Oh, and another example of This one does have some higher pressures with some lower flows, but this is a rotary vane pump. You can see they have a particular pump manufacturer, Procon, or Fluiditech is another name for them. I believe they're the same company. They have what's called a sliding vane impeller. And so this vane is going back and forth while the pump is spinning. And what it's doing is it's forcing the water from one end, it's being pushed out the other, and then the water that replaces it keeps continuously pushing out. Now this works, except that you have sliding parts that will wear out. Usually these are graphite with a rubber lining that are pushing the water, and those both wear out. And they also cause that pulsation that I was talking about. So with the pulsation, you'll get a pattern that's kind of a wave of flow, where with the regenerative turbine, because it's going in this helical motion all the way around, you'll get a nice smooth flow all the way across the board. So some of the minimum information we need when we talk about regenerative turbine pumps, and most pumps for that matter, is we need to know what pressure is needed, what flow is needed, the temperature, if it's going to be a higher temperature or lower temperature. And then one of the main requirements of a regenerative turbine pump is that it has to be clean fluid. Because of those tight tolerances between the impeller wall and the water in the wall before the water channel, debris can get caught in there and lock up a pump pretty easily. So it has to be clean fluids. We're going to talk mostly about water for the selection today. Anything else besides water changes some of the specific gravity, viscosity, things like that. We have 2 application engineers on staff full-time that if it's other than water, you can consult them and they will help you make a selection based on the fluid and temperature. But just for reference, 1 PSI is 2.31 feet a head. And then we also can convert it into meters, which is 0.3048, or bar, which is 0.0689. I believe head in meters is used in most countries where the metric system is used. I believe bar is used a lot more in Europe than other places. And then we work most of our pumps using gallons per minute, but we can also convert to liters per minute, which all of our curves now are published with both gallons and liters, and head in feet and head in meters. So we have all those already in the curve. And then of course, 212 degrees Fahrenheit is boiling water, which is 100 degrees Celsius, which is 373.15 Kelvin. I don't even know anybody who uses Kelvin, but there is a conversion for it. So when we look at MTH models, we have a P31 or T31, which are basically 3-inch impellers. They get up to 150 PSI, 215 PSI, doing very low gallons per minute. So 1 to 5 here, half a gallon a minute to 11 here. And then we start getting larger from there. These are our 2 smallest pumps. So then we have our T41, T51, 4-inch and 5-inch. And then we have our M series, which are multi-stage T51 pumps. So anything that after the T51, when you start adding stages, these are the ones that can get up to the 1,000 PSI, which converts to 2,300 feet. So they can do some pretty high pressures. And then we get into our flex coupled. Flex coupled means that it comes as a pump only with a shaft sticking out of it. You have to use a coupling guard and a motor on a base to be able to drive it. We can supply all of that, or we can supply just the pump only. We have those options. And then when you add an inducer for lower NPSH, which we will get into the MPSH a little more, but when you add that inducer, it's an extra impeller that drops the NPSH to be extremely low, so that you can run water that is sometimes even above boiling. You can still pump it. And so we have a 140, 180, and then the 150, 160, 170, and all those can be turned into 200 series. And then we also do have a few centrifugal pumps that we manufacture. It's a 4-inch, 5-inch, and 6-inch centrifugal pump. They only go up to about 65 psi or 150 feet, but they can hit over 100 gallons a minute just in that small footprint. So when we talk about selection, there's a couple methods you can go about it. We have a couple of selection charts on our website that you can get access to. In this example, we have the boiler feed selection table, and it's very basic. If you know what your boiler horsepower is, in this example, we have 30 boiler horsepower, and you know what the pressure of your boiler system is, in this case it's 50 psi, then the selection that would be ideal for these two cross over to be a T31 on a 3rd horsepower motor. And we can go all the way up the line with all of our flex coupled pumps. And then we can also do the same thing with our, that was close coupled pumps. We can do the same thing with our flex coupled pumps. So here we have the PSI and the boiler horsepower. And so here we've got 15 PSI at a 25 horsepower boiler. I believe this evaporation rate is a certain percentage of the overall boiler horsepower. I'm not exactly sure on the math for that, but the engineers put this together for us, so I don't really need to know. But what I do know is that this particular pump would be a 141D, and it would need a 3rd horsepower to drive it. We also have available on our website is a Jockey pump. Some people know them as pressure maintenance pumps. What it is when you have a fire system. Fire system has a very large pump that can produce hundreds, if not thousands of gallons a minute in the event of a fire to be able to dump out onto the sprinkler system to put out the fire. You need 10% of that to be able to repressurize the system as needed, so that you can, if there's any kind of backflow, or if it's a large building that has piping that may be dripping somewhere, in any case, you need to maintain that pressure so you don't set off those sprinklers. So you need a Jockey pump to do that. So in this selection here, we have the system at 110 psi. This is how much pressure is in those lines, in all that piping that the sprinklers are being held closed with. And if it's 1,000 gallon a minute pump rating for that big pump, the little pump that you would need for the pressure maintenance would be 10 gallons a minute. So here we've got T41L bronze fit, and you would need 1.5 horses to be able to drive that. So on our website, we do have a cross-reference chart. So if you're just doing a replacement for another pump company, if we have experienced replacing those pumps before, we will publish the crossover that would be the ideal MTH pump to hydraulically match. When I say hydraulically match, that means we can hit the same performances. There will probably be, more than likely, some repiping involved. We will not have the same inlets and discharges, but we'll be able to do the same performances. So Right now, I'm actually working on updating our Aurora pump cross-reference charts so that you will be able to see what the Aurora pump curve looks like on top of our MTH curve. Doing the same thing for the Burks. The CR, CT, and CS are basically the equivalent of our T31, T41, and T51. And I've got a few other pump companies that I've been working on. There's an Italian pump company called Semeco that I'm working on a crossover chart for that one. We'll be doing spec eventually. So there's going to be a number of cross-reference selections that'll be available. But for right now, this is what's available on the internet right now. So here we're going to look at a Burks replacement. In this case, one of the more common pumps that Burks sells, probably their biggest seller, is the 7CT7M. On our website, you can simply go look up the 7CT7M and then go straight across to see that it's a T41E on a 3/4 horse. This one's single phase at 3,500 RPM, and it's an open drip proof motor. If it's got a 3 in front of it, so if it was like a 7CT7M, then that would be a 3-phase. But these are all single phase. Here you can see the differences between the two pumps to see how they cross over. With our pump, the T41 has a pretty straight curve, and we put the horsepower dots on here to show you that at this point you would only need a 1/2 horsepower. As you increase the pressure, it gets up to 1 horse. There's a 3/4 in here where the Burks pump has a little bit lower performance curve to it. The other thing about Burks pumps is that they only utilize one side of their impeller. All the work is done on one side of the impeller, so it has some axial thrust, and it performs a little differently. It's got their NPSH numbers aren't as good. This is an NPSH curve. Basically means that when this pump only has 12 feet of NPSH available, this is what the performance would be at 7 feet, at 4 feet. So at 4 feet, we're still able to do several or most of the original performance, to just start losing some performance, where the Burks is almost cut in half from its original performance. We'll look at Aurora here. Aurora is one of the ones where I'm working on doing some overlays of our curves with their curves. Not ready yet, but it will be soon. Here in this example, we have the Aurora K5, which I believe is from their 130 series, would cross over with a 151K. It's our understanding that Aurora is no longer producing 2-stage pumps. So we have seen an uptick in Aurora replacements lately. So this chart has been getting used more and more. And it's also one of the driving factors of why I'm working on the actual individual curve showing how our pump works in comparison to the Aurora pump. So that's coming pretty soon. Now we'll get into some individual pump selection. We're going to start with the single phase pump, or the single stage pumps. And for this example, or for this exercise, and it'll be for the next couple of pumps, we're going to look at 5 gallons a minute at 300 feet ahead. So when you're on our website, when you go to a T51 curve page, the first thing you see is a composite curve. When you're on the website, these highlight which curve you're on. We know we need 300 feet. We know we need about 5 gallons a minute. So in this case, the D fits pretty well. So when you click on the D, what ends up happening is it opens up the individual curve for that D. So here we said we needed 300 gallons a minute. the ideal selection for any regenerative turbine pump is if you imagine that this curve goes all the way to 0. At 50% of the curve from 0 to its run out, the maximum gallons here is about 7.5. That's called run out. From 50% to 80% is where the highest efficiencies are for most of the regenerative turbine pumps. So you always want to make a selection within the 50 to 80%. If you can help it, that will keep the lowest horsepower. It will be the most efficient, have the best NPSH, so on and so forth. So we're looking at our 300 feet. With the T51D here, it does 5.5 horsepower, or 5.5 gallons a minute. To figure out the horsepower, we look at our 300 feet where it hits the main head capacity curve. You go down to the horsepower line, which is called brake horsepower, and then you go across, and this particular pump needs just under 1.0 brake horsepower, which means you would need to use a 1 horsepower motor. If you want to know what the efficiency is, doing the same method, going across from that 300, where it intersects, you go up and you go across, and you see that this pump does 44% efficiency. Now, 44% efficiency sounds like it's not very efficient. But the truth of the matter is, when you look at it, the comparison of it to a centrifugal pump, which a single stage centrifugal pump will do sometimes 70 or 80% efficiency, it sounds like the centrifugal pump is the way to go. But when you start adding those impellers to that centrifugal pump, you start losing that efficiency. And so what ends up happening is you have, it still publishes the higher efficiency percentage, but you're using a higher horsepower to drive it. So in a lot of cases, the same pressure that we would be using a 1 horsepower motor for, a multi-stage centrifugal may be using 1.5, 2, maybe even 3 horsepower to do the same job. So you're physically using a smaller motor, which is using less electricity. So in essence, it's more efficient. So we're going to talk a little bit about NPSH. So NPSH is net positive suction head. At normal temperature, the NPSH of water by itself is 32 feet of head. That means that if you're at sea level and you have a bucket of water and you put a pressure sensor at the bottom of that bucket, you automatically have 32 feet or 32 feet of pressure, or 14 psi, just from the weight of the water. So as you start increasing the pressure or increasing the temperature, that NPSH starts to go away. So most pumps can handle from ambient temperature, which is anything below 90 degrees, all the way up to 150 or so. When it starts hitting about 180, 180 is when you start getting to where it's only 16 feet. Now you're going to start seeing some pumps that can't handle it. What happens is at that 16 feet, if the pump doesn't have enough NPSH, the water will boil even below the boiling temperature, which is normally 212. And those bubbles will make the pump stop working. That's what cavitation is. When you start getting into really high temperatures, 200 degrees, you only have 6 feet. At 212 degrees boiling, you have 0 feet of NPSH. It just does not have any energy in it. As soon as the impeller touches it, it starts boiling, and the bubbles are more than the pump can move. So you have basically zero energy to your water. So when we look at NPSH here, if you have a tank that has 4 feet of water in it, that's 4 feet above your pump, you have your 32 feet of NPSH available, plus the 4 feet that the water is above the tank. When you start heating that water up around 207 to 208, the tank has 4 feet of NPSH, but the water only has 3 feet of NPSH, so you have about 7 feet of NPSH available. When you get to that point, you're 300 gallons a minute. Instead of doing the original 5.5 gallons a minute that you wanted, it only has that 7 feet of NPSH. The performance will start to degrade because the bubbles from the boiling water are pushing or are compensating for how much fluid can fit inside the pump, and so the amount of fluid being moved is less. So when you hit 7 feet, you're at you're only doing about 5.2 gallons a minute. When we get to the point where the water is boiling, it has the 0 NPSH atmospherically. If there's 4 feet of water in the tank and this water is boiling, you only have 4 feet of NPSH. When you have 4 feet of NPSH, the performance degrades quite a bit. So at 4 feet of NPSH, you will only get 4.5 gallons a minute instead of your original 5.5 gallons a minute. But the pump will continue to run. Centrifugal pumps, when it hits boiling, those bubbles from the boiling water build up at the eye of the impeller and don't allow any water to pass. That's the cavitation. That's when the pumps will not perform anymore. They just cease performing until they cool off. Just so you know, we do have a version of our pumps in a Sealless can version. That means that there's no mechanical seals to it. Just to show you the differences, we have a mechanical seal. That's where these two faces have a very thin barrier of water that prevent water from going from the inside of the pump to the outside. With a regenerative turbine pump, the entire pump is sealed shut, and the fluid is allowed to go into the inlet, and then it goes across the bearings here, goes across a very thin lining, and then goes down through the back bearing, and then it enters a hollow shaft impeller that goes all the way to the front and cycles it back out to the outside of the to the discharge of the pump. So with most Sealless regenerative turbine pumps, you lose maybe half a gallon a minute to this flow, but they are super quiet and they can't leak because they don't have any method for fluid to get outside unless they're so overpressured that you blow out a seal, but that doesn't happen too often. So looking at that same 300 feet, we wanted to get 5 gallons a minute, and you can see that we can't quite do it. Using an E here, we can't quite get that 5.5 gallons a minute, or 5 gallons a minute, but with all of our Sealless pumps, they're all VFD compatible. So in this case, to get your 5 gallons a minute, you'd have to go a little bit higher than the 60 hertz, estimated about 65 hertz. And then at 60 hertz, you'd only get 4.2 gallons a minute. But if you sped the pump up, you could get it back up to the 5 gallons a minute, no problem. And here we publish the amps instead of the horsepower. It would estimate about 65 hertz again to be able to hit that, and it would be pulling a little over 6 amps. Moving on to some flex coupled pumps. With the flex coupled pumps, because we have so many combinations of 1 stage through 4 stage and all the models, it would be hard to put a family composite curve of the flex coupled pumps on top of each other, because you would see multiple lines crossing over each other. So what we've done is we've put together this table based on your pressure, which this is in head and feet, and your head and feet, and then your flow, which is your gallons per minute. And we've made it so that we've pre-selected the most efficient pump at that pressure and flow. So here we're looking at 75 feet ahead, 8 gallons a minute, a 141E with half horsepower is ideal. With the larger 150, 160, 170 models, they have higher pressures. So here we're looking at 150 gallons a minute at, 150 PS or head and feet with 40 gallons a minute. And we're looking at a 151L on a 5-horse motor. We'll look at individual curves. We have a head scale, which is the head in meters and head in feet. We have an NPSH scale, which we also have in feet and meters. And then we have the horsepower scale is separate from the first curve. So we publish the curve with just the performance, the head capacity performance on one curve along with the NPSH. And then on a completely different curve, we put the horsepower scale. We do this so that these lines don't cross each other and it gets confusing. So we publish the horsepower at the chart below, and then of course going across is your gallons per minute or liters per minute. So again, just like a single stage regenerative turbine, because it's any regenerative turbine, half of or 50% of the overall performance curve, if this curve went all the way up to 0, we'd be from 0 to a little bit past 10 gallons a minute. So a little bit past 5 gallons a minute is 50%. A little past 8 gallons a minute is 80%. So here we're looking at our same 5 gallons a minute at 300 feet ahead. We have a 140 Series E, and here we go across. So we see there's the two stage. Each curve, when you add stages, only adds pressure, does not add flow. So for this pump to get that 300 feet at the 5 gallons a minute, the 2 stage is going to be the ideal selection. It's going to do just over 5 gallons a minute. And then to determine the horsepower, it's the same method as with the single stage, except that the curve is on a different chart. We keep the gallons per minute scale the same, so you can go straight across 300 gallons a minute or 300 feet ahead. You're just over 5 gallons a minute, straight down to your horsepower. And again, you have to use the corresponding number of stages. And we have our 2 stage. So the horsepower required is about 1.3 horsepower. So you would need to use a 1.5 horse motor to be able to drive this. So when we look at the NPSH on these flex coupled pumps, because we can add this extra stage with this extra impeller, this is a centrifugal style impeller that ramps up the speed of the water being introduced to the regenerative turbines to be able to lower the NPSH. So with a typical 100 series, you have a NPSH curve that goes up, and where the run out is a little bit below 40 feet. When you add, and this is going to be for mostly boiling water, when you get to a point where your water is really high temperature and you don't have 30 feet of NPSH available or 40 feet, you need lower NPSH, you can use one of these inducers, making it a 200 series, to drop that NPSH down to about 2 feet all the way across. and each pump is different, but we put the curves on every pump so you can see what the NPSH will be. So looking at the same curve we were looking at, our 300 feet, when you go down and you look at the horsepower here, it was at the just under 1.5 horsepower. But when you look at the NPSH with a 100 series, you have just over 3 feet. With a 200 series, it can drop that 3 feet down to 1 foot. So you can have 1 foot of NPSH with that. But you have to add a 0.5 horsepower to help drive that that inducer impeller to compensate for the amount of power that it would use. So what happens is, even though you only needed 1.5 horses when it was just a 100 series, when you make it a 200 series, it actually jumps that 0.5 horsepower up above the 1.5, so you have to go up to a 2 horsepower motor. And then when we look at M series are basically T51 pumps that have multiple stages to them. So if you'll notice, if you're familiar with how our models look, you'll notice the motor bracket is a T51 motor bracket, and it has a different casing on the front of it to make it almost inline, so that you can have just a single line going in one end and out the other. But when you start adding stages to it, they get taller and they get more pressure, higher abilities. So they come in both vertical and horizontal. So here we're looking at 1,000 gallon or 1,000 feet ahead. At the 1,000 feet ahead, we're going to look at this particular pump, an M50. In this case, it's 3 stages. M53 is going to do about 7.5 gallons a minute. Just like the 100 and 200 series, your NPSH can be changed by adding an inducer. When you add an inducer to an M series, it becomes an L series, adding that inducer. So you have your M53 or L53. It just changes the NPSH. So here we do the same methods. You add a 0.5 horse if you're going to add the inducer. So in this case, we need a 5 horsepower motor to be able to run it with just the M series. If you add that L series, it makes it a little bit higher, so you need the 7.5, which is the next increment. And then next we have relief valves. If you have to maintain a certain pressure, but your flows are going to change, or you need a safety for not deadheading the pump, because you cannot deadhead a regenerative turbine pump, we do have pressure relief valves. So if the relief valve is set at 100 psi, a 1/2-inch relief valve can divert up to 12 gallons a minute, and so on and so forth. So when you hit these pressures, it changes the flows so that you can have a controlled pressure so that it won't exceed. So, and then I had mentioned earlier, we do have a line of centrifugal pumps. The centrifugal pumps are pretty straightforward, but they do have a unique design that we do not do trims with them. Instead, we have them set up so that each pump has its own horsepower rating, and we supply the horsepower motors that go with these C-Series pumps. So this C-Series will actually do all the way from shutoff to run out, and will not overamp this 1/2 horsepower motor. So you can keep it shut off. It won't hurt the pump. It's probably not great for the steel, but you can go all the way to run out without having to change the horsepower. And that is about all I had. And I'm seeing when selecting multi-stage pump, what happens when the flow pressure falls in between stages. Well, when it falls in between stages, we'll go back and look. So when it's in between stages, like say you only needed your 1,000 feet of head, but you only needed 7 gallons a minute. You always select it for the 1,000 feet ahead, and you just have it produce half a gallon more a minute. So you always select it for the higher curve. If you select it for the lower curve, then the pump is only going to produce the 6 gallons a minute. And if you needed that 7 gallons a minute for the piece of equipment you're running, you need to go to the next higher pump. It doesn't really make a difference usually with just adding a couple gallons a minute, give or take. There aren't too many precise pieces of machine that can't handle that. The only time we really run into where it has to be precise is when you're using it for temperature control, where you're pushing a fluid or a refrigerant through a piece of equipment that has to maintain the same temperature within 1/4 of a degree. Then you need a precise flow, which is why we have so many different models of our close coupled and flex coupled, so that you can precisely tune in exactly what you need. So hopefully that answered the question. Bob, did you have anything you wanted to add? You're muted.
And the subject you're just talking about here, and if you need it really precise, we are seeing a tremendous amount of our pumps being used with VFD controls. A regenerative turbine pump, you can speed it up, slow it down with a VFD control, as long as you have the correct motor on it. And you can tune it in to exactly the point you want. Many of our OEM manufacturers that we sell to especially will use the VFD. Now, Scott, if I could go ahead and expand on that a little bit.
Sure.
When we get into our larger pumps, like the 170 series, 160 series, we do have on the website variable speed curves, various speeds, where you can take the like the 170 series, which is a 1750 RPM pump, is what's published, which can turn up to 2900 RPM, but you use a VFD and with a 3450 RPM motor, and you can increase the flow, you can increase the pressure using that VFD. So keep in mind the possibility on some of your jobs, if the performance is not exact on the curve, is not exactly what you're looking for, the addition of VFD will open that up and you can hit a broader range. That's about it, Scott. You've done a good job.
Well, nobody else had any questions. And that looks like that was just the one question we had. I really appreciate you guys taking the time out of your day for this. If you need any follow-up questions, please feel free to contact me. You can either call my phone or you can email me, which I think most of you have my email because you got the invites for this. So please feel free to email me if you have any questions. Otherwise, enjoy the rest of your day, and thanks for watching.
Thanks, Scott.